very much.
Indeed. So our next speaker is Luka Peternel, who I see is already in the call, and we are perfectly on time. So it's my pleasure to introduce you, Luka Peternel, an assistant professor at the Department of Cognitive Robotics at Delft University of Technology in the Netherlands. And Luka received his PhD in robotics in 2015 from the University of Ljubljana. So I think he would have enjoyed even more than us to be in Ljubljana today. And he worked in the Department of for Automation, Biocybernetics, and Robotics of the Josef Stefan Institute. He has worked in the Department of Brain-Robot Interface, ATR Computational Neuroscience Laboratories in Kyoto, Japan, in 2013 and 2014, and finally in the Human Robot Interface and Physical Interaction Lab at the Italian Institute of Technology from 2015 to 2018. So today, I think he's going to tell us about robot control and learning methods for co-manipulation with humans. And Luka, you should already be able to share your screen. I remind you that you have 25 minutes, and I'll give you a 2-minute warning. 2-minute warning, yeah. So whenever you're ready, the floor is yours.
Yeah, thank you very much for this introduction. Let me share my slides now. Is it visible?
Yes.
Perfect. Okay, so as it was mentioned in introduction, yeah, I've been through many places, but at the moment I'm an assistant professor at TU Delft in Netherlands. And yeah, today, like mentioned in the introduction, I'll talk about ergonomic control of human-robot co-manipulation. Okay, the first thing, introduction and a bit of motivation. So why human-robot collaboration? So we have on one side robots who are super fast and super precise and also powerful. And we have on the other side humans who have still very much superior cognitive capabilities and are very good at adapting new situations. So, and what we want to do is actually combine these two advantages of both types of agents to produce various complicated tasks. So I actually, maybe I can just quickly answer or give my opinion on the one interesting question in the chat. I think it was from Ayush. So he asked what's the difference between learning for autonomous robot behavior and learning for human-robot collaboration. So for human-robot collaboration, the main challenge is that you have another agent affecting the task and you have no control over that agent. So for example, if you are learning for the robot, there is human there that is going to do whatever the human is going to do, and the robot has to just continuously adapt to new humans. So if you teach the robot to do something with one user and then the user changes, the behavior also has to change typically. But mostly today, yeah, since the workshop is about safety, I'll focus on ergonomics for the humans. So there are many aspects of ergonomics, but I'll start with the very basic ones. So these are very basic principles of mechanical engineering. So first is impedance. So impedance is a way to simplify the interaction between different objects, also human and robot. So the impedance basically gives us a relationship between the motion and forces that are experienced during the interaction and can help us with task performance, but also safety. So if you make the robot softer, then the human interacting with the robot will be intrinsically much safer to that. And yeah, the impedance we typically represent with ellipsoids. So Silvan already mentioned some of the ellipsoids. Here is a stiffness ellipsoid changing in the solving task. But we also have manipulability ellipsoid, which was also mentioned by Silvan, which we have force and velocity manipulability. And manipulability is also a very fundamental mechanical property of any kind of structure, not just robots and humans, also also buildings have, in a sense, manipulability. And it kind of gives you the idea between how the joint variables translate into endpoint variables. So if you are producing velocities in the joints, how will produce how this velocity will reflect on the velocity of the endpoint, and same for the forces. So how the torques in the joint will reflect on the forces on the endpoint. And the configuration plays a crucial role in this transformation. So if you have extended structure or extended arm, if I'm trying to push in this direction, I'll have very resistive structure because the whole structure opposes this force. So even if I try to control a compliant robot in that direction, if I'm in this singular configuration, the robot will still be stiff. So actually the compliance is a combination of manipulability and the actively controlled impedance. So we have to consider both. And in these frameworks that we developed, we always consider both of these basic mechanical properties, which are also then related to the safety of the human. So in this case, we first try to develop some model that can translate the muscle activity into the endpoint forces or movements. So let's say we want to know which muscles are predominantly activated if the human is polishing this by pushing up. So now the human is producing endpoint force up, and certain muscles will get tired, and the robot can detect this and then reconfigure the task execution in order that the other fresh muscles are involved and the tired now can rest because another set of muscles is active. And of course, we give this knowledge to the robot so that it has knowledge about this transformation between joint space and endpoint space. And this can make the human task execution much more ergonomic because it can always stay fresh during the execution. So in another case, we examined how to combine multiple ergonomic matrices. So I already mentioned manipulability, but there's also joint torque and also fatigue, which then in the end exhibits as an endurance time during the task execution. So, and we want to be able to combine these matrices for different tasks, because different tasks, for example, drilling, only several are important, and for assembly, another set of matrices are important, and we develop this artificial intelligence that can kind of detect this and then appropriately use different matrices. And then also we can label the workspace of the human-robot interaction in a way that the robot can easily understand which parts of the workspace, which configurations are actually good for the human. And you can see that we also consider redundancy of the human arm. So even if you might be in a green endpoint spot, there might be some configurations, because human has redundancy, that are not actually green zone in terms of ergonomics. And then we have we develop kind of different kind of maps that can give different functionalities. So like continuous gives you more information, but then again does not respect the thresholds. So you never know whether one of the matrices that we use exceeds the threshold, which can be done by the binary map. And then the trade-off between both is a hybrid binary continuous map that can take advantages of both. So here is one work that we use ergonomic models in the robot control. So here the robot detected, okay, in this arm configuration, human has the best manipulability and the least joint torques for producing this collaborative polishing task. and then again hand over. So the robot could hand over like in this configuration, which is very convenient for the robot, but we don't care too much about the robot. We care more about the human. So the robot should bring it to a configuration where it's convenient for the human workers. Then we can translate this principle also to teleoperation. For example, here we also have the teleoperation system has this ergonomics model inside the control. And let's say in this human now produces this force production task in a very bad configuration. You see here teleoperator. And then the robot detects that this is not good through the fatigue model. And then the teleoperation system temporarily decouples the haptic device from the remote robot and then reconfigures the human into a better configuration, and then recouples the haptic device to the remote robot, and then the human can resume the task execution. Yeah, this is very similar, so I'll just skip that one. So we were talking now about human, but also robots should be safe in that sense. So in this case, we are considering a robot joint fatigue. So this is related to the thermal fatigue of the motors. So when the robot produces some very heavy lifting tasks, so in this case, it has to hold this tool and also has to produce the polishing force, while the human basically just control compliantly the position of the polishing. But the robot is the one that is exerting most of the effort. So the robot will get tired. And we actually use the redundancy of the robot to kind of try to reconfigure the robotic arm so that the tired joint, so in this case, this joint became the most tired. We will try to reconfigure it in a way that now it's not involved so much. So now this joint is basically in the same direction. The axis of this joint is the same direction as the gravity, so that the tool carrying is now taken over by other joints of the robot. So yeah, we were trying to prevent human from getting injured, or we're trying to maintain safety. But no matter what you do, in the end, there will always be some mistakes and some unpredictable events that will happen, and humans will still get injured, even though we try to minimize it. So in that case, you might have some muscle tears or some other injuries, and workers will need recovery and physiotherapy. So in this case, in this work, we examined especially the shoulder tears, which are very, very common, especially in more elderly people, and how this proceeds, how the rehabilitation proceeds. So first, it's done by surgery. So the surgeon stitches the torn muscles together. These are these rotator cuff muscles that hold the shoulder in place. And then it's followed by a very lengthy physiotherapy, which is still the state of the art, is that the human physiotherapy guides the patient through various poses so that it can stimulate the rehabilitation. But the problem is that physiotherapists, humans, we can only rely on our experience and qualitative data. So the physiotherapist, no matter how experienced, will never know for sure what's happening inside the shoulder, because it doesn't have the quantitative information or quantitative measurements and model. So what we do here, we actually add this quantitative part in form of a model and measurement through the robotic physiotherapy system. And then this system has the insight of inner working of the human body, and therefore can be less conservative. So human physiotherapists have to be quite conservative with the therapy, because they don't want to re-tear the muscles. and thus they have to consider this part of the safety. But the robot knows exactly what the strains are in different configuration, and therefore can improve the range of motion, and range of motion is actually related to the speed of recovery. So if you do more range of motion, you will recover quicker. So that's what we are aiming for. So the underlying part of this method is the strain map. So the robot knows exactly in what configuration of the arm, what kind of strain the muscles have. And of course, rotator cuff are composed of 4 muscles, and we can have individual 4 and also combined 4. And then we can plan the physiotherapy so that we can maximize the safety and at the same time range of motion. Yeah, here's just a short video of this physiotherapy. So here again, this is the strain map, and this is the trajectory that we form. So we don't need to have trajectory. So in this case, we use trajectories. But in the later stages, the human can actually perform this by themselves. And we use this strain map to kind of restrict humans from entering those regions. See now, it's moving it. And those strain maps, they are actually in the muscle space. So they are not in endpoint space. So what you're seeing was the basically shoulder joint configuration. But shoulder is a ball socket, so it might be a bit difficult to have the nice visual interpretation. Okay, now I'll switch the topic a bit. I'll go into ergonomics in teleimpedance. So what is teleimpedance? Teleimpedance is basically teleoperation with additional channel that enables the teleoperator to also command the impedance of the remote robot. So to make it soft and stiff, which is very important for the interaction. So in some cases, you have to be soft and stiff. So in this drilling case, you should be stiff in the plane of the drilling to actually control precisely the drilling position, but then you should be more compliant in the direction of the drilling, so you can be safer, and you also have this more what I call is sensitivity to the force controller. So you have to move further inside the object, your reference, to produce the force, and this force variation then also are less. But originally the teleimpedance was proposed without force feedback, but we want to introduce force feedback because that not only allows us to sense the environment to be more safe, but also we can sense what kind of impedance we actually command, because we can feel how soft or stiff the robot is. But then, yeah, okay, let me show you first a few videos of this. So in this case, we perform the teaching of some assembly tasks, so teaching through teleoperation. So now the human is teaching, and that thing held here is the device, an interface that actually allows the human to command the impedance. So the more you push the button in, the more stiffer the robot becomes, and vice versa. But in this case, okay, now the learning is done. Now the robot will produce this autonomously. So in this case, when you try to insert, you have to become softer so that the operation is smoother, so it easily fits inside the groove. But when you slide in, we keep the robot compliant. And why we keep it compliant? Because the environment already provides the stabilization. So you don't need to be stiff because you will already be precise. And another part is if something gets displaced or some anomaly appears, you will break the part or the robot if you're stiff. But if you are compliant, for example, in just a second, you will see some form of human-robot collaboration. yeah, you can see now the robot is safe if you taught it to be compliant aside. Okay, I'm moving forward now. Okay, there are many interfaces in the literature for the teleimpedance, so to command the impedance. So like this push button, grip sensor, or even complicated version which is EMG, which measures muscle activity to estimate the human impedance. But for example, if you use force feedback with the EMG, then you have something we call force feedback coupling. So whatever let's say your force feedback will slightly perturb your arm, and this will cause a reflex to unnaturally stiffen up your arm. And this might be dangerous if you want the robot to be soft, and then suddenly you automatically stiffen up your arm, and that is sent as a command to the robot. That could be dangerous. And we actually examine this effect. So the commanded impedance is actually the intended impedance that you try to command with your arm, plus the reflex change related to the reflexes. Yeah, we investigated this effect. So we use one interface that is coupled, which is, for example, muscle activity measurement based. So we would let the operator, so this was user study, would let them control something with the remote robot, and then we would suddenly perturb them and observe what's happening. And then we did the same thing with the decoupled interface. So for example, this push button, you can hold it in the other arm, and the reflexes will not affect your impedance. But it's not like a one-way street. So both has some advantages and disadvantages. So the advantage of the coupled is that if you actually want to counteract some unexpected perturbation, it will help you. But if you want to become stiff, but if you want to be compliant, but something is making you stiff because of the reflexes, then it's not good. So yeah, it's a trade-off that you have to consider regarding the task. And you can see that the muscle activity interface has this kind of neuromechanical coupling, which kind of gives away some of the control over the degrees of freedom that you can command to the stiffness based on the interaction with the environment. So we wanted to decouple this and also make it simple. So similar to what Sylvain was showing, how to teach a robot with a smartphone. So this is kind of similar. We can use some tablet to kind of manipulate with your fingers the ellipsoid at the end point of the remote robot. So this is kind of decoupled interface, and we can still control multiple axis of the ellipsoid, because on the push button you can only control 1 degree of freedom at any given time, but here you can control it in different directions. So this is in 3D, so this is one plane and this is the other plane, so we can control the 3D ellipsoid. Yeah, in light of time, I'll just show a little bit of an experiment here. So this will also be presented at on Wednesday at MPC and Dynamic Control session. So if you have time, you can drop by. Yeah, this is how it looks like. You can, but then sometimes in commanding the impedance consciously can be quite a big cognitive load for the operator. So we developed a new interface that's vision-based. So the robot is semi-autonomous. So the human commands the motion, but the robot automatically changes the impedance based on the detected object. So if you have a metal, we would prescribe some stiffness. If you have a rubber, you would prescribe a different stiffness. If you have a glass, you would prescribe another stiffness. And of course, for glass, this is quite important because you want to be safe. You don't want to break something. And the robot can do this automatically. So when the human approaches some object, the robot recognizes, okay, the human wants to interact with that object. Then it will adjust the stiffness. And it also works for external perturbation, as you can see here. So now when the robot detects that some perturbation is coming, it will stiffen up in that direction.
So Luka, just a reminder, you have 2 minutes left.
Yeah, I will. I think that's the last video anyway. And this work will be presented in a parallel session to that one from before. And yeah, you can see for a metal, you can be quite stiff in order to kind of match impedances. For glass, you want to be very compliant, because these materials, we have different properties like elasticity and fragility. We consider different properties on the robot side, and then the robot, based on this combination of these properties, tries to set the right impedance. Yeah, thank you for your attention, and these are some of the co-authors that I would like to also acknowledge. Any questions?
Thank you, Luka, for the very interesting talk. So I think we have one question already in the chat from Valeria, who was asking, have you considered the use of other physiological measurements in addition to EMG to assess users' fatigue and/or ergonomics of human-robot collaboration systems? For example, she was thinking of cardiac, brain, or electrodermal activity.
No, not really. I mean, we were interested in considering many of them. Also, so when you are, how often you blink and for how long you blink is also another nice one. But we wanted to move away from these that require any kind of measurements, because for industrial cases, they are very impractical. So now our push is to move toward model-based, because model doesn't cost anything. Okay, you need some time to adjust it for a subject, but then when you have it adjusted, you can use it. And there are no annoying wearable devices, no sensor assistant that you always have to calibrate and look into it. Yeah, that's the main reason why we didn't try these ones.
Sounds good. And I also had a curiosity, if there are no other questions in the chat, regarding the safe physical therapy for shoulder rehabilitation work. Like, have you done some studies to quantitatively verify the safety or quantify the patient safety, and also evaluate the efficacy of this robot-aided?
Yeah, that's a good question. So unfortunately, not yet, but we are on the way to do that. So this was just a proof of concept study, but then first we want to test it on the human subjects, so healthy human subjects. And then second, we want to then move it to hospitals to do it first on limited patient study, and then full efficacy test on multiple patients. So we are already connected with some hospital in the Netherlands, for example, with Erasmus Hospital in Rotterdam, or the medical center in Leiden.
Very nice. Okay. All right, so I think there are no other questions. So thank you once again, Luka.
Yeah, thank you for inviting me.
Thanks. And we can, I think now next in the workshop is what we call breakfast, lunch, dinner, break, from depending on wherever you are tuning in from. So I think we will rejoin in 50 minutes, so 1:10 p.m. in the Central European Time, with the accepted paper presentation. So stay tuned for that, and see you in a bit.